Okay. Hello, everyone. Welcome to the lecture number 14, 14 or 15. I don't remember which one, but whatever the case, previously, previously we were finishing up the our story about dynamics of thermalization, right? And we concluded with this. Uh, I concluded with this funny physical interpretation of thermalization as a this infectious disease, right? Where the term a system in a thermal state comes into contact with other systems that are, innocent, not infected yet. They come into contact. The thermal bath infects the healthy system. It becomes sick, becomes goes into thermal equilibrium, and then I said that the system, the newly infected system, is now a carrier of the disease, right? And it can pass it on uh, to other unsuspecting healthy systems. So like like a zombie virus or something. And and the thing about that story, it was maybe a little bit over the top, but strictly speaking, right? I mentioned that. Oh, here's the sketch from previous week, right? That we described the process of thermalization when we saw the process of thermalization, right? We analyze it. So when the bath comes into contact with system S, we saw how it does it infection spreads the infection to system S, but haven't really seen we weren't able to describe if this newly infected system S was actually able to spread the thermalization further, right? Mm. So this is the thing I want to talk about today, because as it turns out, to capture this kind of feature, and not only that feature, but actually quite a lot of different problems, you need something that's let me call this like I wrote here. You need to be able to describe multi-time correlation functions in open systems specifically. Because in closed system it's easy, but in open system it's a new challenge. Okay, and yeah, and this will require to do this thing. It's a new chapter 7, because this will require from us to like expand our theory of open systems. So, okay, our understanding of dynamical maps, where they come from, how to calculate them, and how they work, how they generate dynamics. This won't be sufficient, okay, to describe multi-time correlations. So the things that I will be talking about today, they are based on a very recent paper that's currently undergoing review in SciPost. So you can find it. If you want to see, more details about it, you can go to the primary source, which is of course, there is stuff in the notes, right? On the lecture notes, we have on a website, but if you want, to see the primary source, go either here to SciPost or straight to archive, and uh, and expect some updates, because if the referee and reviewer keep up their deadline, I should have all the reviews by the end of the month. So I will have to update the paper. So it's again, as everything here is in like ongoing projects. But yeah, so this is the primary source, but You can also check out the lecture notes. All right. So what are those multi-time correlation functions I'm talking about here? So mm, rather than giving you this like a rather than starting with some formal definitions and stuff like that, I think this it's much it will be maybe better. It will allow you to better understand what the problem is. If I start with a story, actually the story of this the problem of spreading thermalization. Okay, so let's get over it again about the issue of the spread, and by doing so we will get to the crux of the problem, right? Which should be a way more efficient way to introduce it uh, for you. Okay, so problem of spreading thermalization. Uh, yeah, so let's start by having a maybe let's do some drawings. So we are starting with our patient zero, okay, the thermal bath. So we have a thermal bath. It's temperature inverse beta, right? So this is do I use B? Yeah. So this would be a system B bath, right? And we want to start by bringing in the first victim. So the first guy who will get infected. Uh, so we bring in a small, very simple system uh, Q because it is a two-level qubit, okay? And we allow guys to we allow the buff to grab it and start interacting with it. So they start to interact. Maybe let's label it qubit. Qubit. So let's define how the interaction goes, and we will pick here a very simple model. So the total Hamiltonian of our pair of the buff and of its victim. So QB, full Hamiltonian, will look something like this: 1 times HB, so the free Hamiltonian of the buff, plus interaction term. Let's say we interact through coupling to Pauli matrix X on the qubit side and some generic coupling B on the buff side. And note I'm cheeky here because I'm setting the free qubit Hamiltonian to 0. Okay, so if you notice HQ is 0 here. Just to make things simple. What else? Oh, and let's initialize our guys. So rho QB at t equals 0. So let's grab on the qubit side, let's take a polarized state. So one of the eigenstates of the sigma z. And on buff side, we will take a thermal state so that we know that the buff is the patient zero, okay? So what is this guy here? So this is rho 0q, okay? And it's defined by, so if we take sigma z acting on up, this is the eigencat with eigenvalue 1. Arrow down would be eigencat with eigenvalue -1. Yeah, so that's the definition. Oh, and of course, just as a reminder, thermal state defined as previously. So it's E2 minus beta. This is where temperature comes in with respect to the energy levels defined by the free Hamiltonian. And of course, the normalization trace over B, E minus beta H B. the normalization, right? We also sometimes call it Z, B beta, statistical sum, right? Like it's called. Uh, so yeah, so that this is our setup. It's kind of simple, right? And one more thing, for simplicity, assume we'll assume just to make it simpler that the average value of the coupling B, uh, P B beta is 0. Okay. Well, let's say we picked our coupling on the buff side such that this average turns out to be 0, so that we don't have to shift the qubit Hamiltonian. We don't have to bother about shifting the qubit Hamiltonian or the coupling, as we used to do previously, right? On previous lectures. What next? Of course, so we want to so we brought our qubit. Right now we want them to buff to thermalize the qubit, infect it, right? So of course we will assume also that the coupling is weak. So lambda TB core, this is much smaller than 1, right? So that we can deploy our Born Markov and all the other approximations to get, so that we can describe the dynamics, what is happening with a qubit state with our favorite Davis map. So in weak coupling regime, we have Davis. How do you write Davis? Don't want to misspell him again. Davis. Okay. Davis. Yeah, I have there's this book. Okay, let me show you. By Davis. It's this Davis we are talking about. Excellent book, by the way. If you can get your hands on it, highly recommend it. It's a lot of math there, but it's fun. It's very well written. Old books are almost always very well written. So we have Davis map, and so if we take, so in other words, if we took the dynamical map generated by with our Hamiltonian, right? Just to remind us, so HQB, this is HQB, right? Acting on some input state on the system and initial thermal state of the buff, right? So we have our weak coupling regime Davis approximation. We can approximate this guy with HTQ, right? There is a free Hamiltonian part minus lambda square T and the Davis generator for qubit, right? But remember, we set this guy to 0, so this simplifies to just the Davis generator, Davis Q. And this guy, we talked about them. We talked about this generator a lot on all the couple of previous lectures. So I will just write down what you get once you do all the approximations, Born Markov, secular, and stuff. So in our case, so again, we have a very simple Hamiltonian here, right? Especially this simplifies a lot. Mm, so the Davis generator would be minus I coefficient JQ 0, because our energy levels at generate, so there is only one frequency in the decomposition after you do all the secular approximations, and only the zero frequency comes up, right? Because all the energy levels have the same value, or all two energy levels for qubit have same value because we set the qubit Hamiltonian to zero. Uh, so we would have this lamp shift here. The coupling is sigma x, right? So we have there is only, because there's only one frequency, and the coupling is of this form. We only have one jump operator, sigma x. By the way, this is sigma Pauli matrices are such that they're Hermitian, of course, so then this dagger doesn't do anything for it. And the Pauli matrix square is just identity one, right? So this commutator with identity is always zero for finite dimensional systems, at least. Uh, so this lamp shift doesn't come up in our this simplistic example. So the only thing we will get is the other part. So we have a transition rate, again, only one frequency, zero frequency is relevant. And the form, again, only one jump operator, sigma x. Minus 1/2, and the anti-commutator x dagger, sigma x bullet. Again, dagger does nothing, right? Because sigmas are Hermitian. This is one, again, one, but this time is anti-commutator, not commutator, so this won't vanish, but it will simplify tremendously anyway. So we will have, oh, sorry, not Q. I'm so sorry. It should be B, because this lamp shift and transition rate, they come from buff. It's crucial. I made made a very stupid mistake here. Okay, this is crucial. They come from, there are half Fourier transforms of correlation functions for buff observables. B0 sigma x. So sandwich with sigma x's minus this anti-commutator, because this reduces to one, so it simplifies to just identity. Okay. So this is a Davis map for our qubit. Very, very simple. I mean, it is for qubit, so it have to be quite simple. There is not many options to complicate it much, but in this case, we even made it even more primitive by our choices regarding the Hamiltonian here. So this is like one of the simplest things you can get. Uh, and what else? What else can I write here? Maybe, you know what? Maybe let me remind you what W is, what transition rate is. Transition rate. Transition rate. So WB of omega, right? Because it's here is W of 0 because only one frequency comes in, but this is a transition rates are functions of frequencies. So it's twice the coupling strength, so lambda 0, and you take a real part of the half of Fourier transform. And what do you transform? Well, you take two-time correlation function of buff coupling. So let me write it like this. T0 plus U, B, H, B, T0 plus U, H, B, U, B. So interaction picture for buff observable, the one that we are coupling to, B beta. Okay, and Fourier transform, so minus I omega U du. I wrote it like that to underline that this is a two-time function. Okay, so we have two times U and some T0 plus U. But because this is a station, the initial state of buff is stationary. That is, P beta commutes with the Hamiltonian, right? So you can eliminate the uh, you can turn this two-time function into a function of time difference, uh, which is U. So this guy, I believe I showed this calculation last week. So this guy simplifies real part omega trace HBU B minus I H BU B. Oh crap, sorry. Again, silly mistake again. U is supposed to be a time difference between two arguments, so I should write it like this. Have T0 and the other time is T0 plus something extra, so that this extra thing is the difference between those two time arguments. So you can like shift everything by this T0 here, and only the difference between arguments survives because it's all stationary. Okay, so that's the transition rate. And the transition rate, it's a buff, so it satisfies detailed balance for us, right? Minus beta omega. Detailed balance. Yay, detailed balance. That was a key ingredient for thermalization. But in our simplistic case, we don't have to bother about this for now, because now the thing is we want to so we have buff, it grabbed the qubit and does its thing, and we want to see that it will thermalize. It will thermalize the qubit. So in other words, let's apply our simple uh, simple map to the initial state of the qubit, which I chose to be this up state. Okay. So we apply it, and a straightforward calculation, which you can do on your as an exercise. You can apply this guy to this state, and you can easily show that as send time to infinity. So asymptotically, this guy will be reduced to 1/2 1 to identity. Okay. Which in our case, it actually coincides with the thermal state. If we even got the shifted sigma x qubit beta, it coincides because everything here is 0. because this is how we chose it. So in our case, identity is actually the same as thermal equilibrium state, which is very convenient for us. Uh, and yeah, so okay, so we have our qubit, we have our buff, and the buff grab the qubit, thermalize it. And now right the question is, okay, so if the thermalization was passed on to qubit, or in other words, or in other way of thinking this is like you can think that the qubit got assimilated into the buff, right? Because now it's a part of the buff. Because I mean, typically when you think about the buff, some complex system, right? So probably composed of many subsystems in it, all the systems it infected previously, the patient zero infected previously, and all those systems are interacting with each other, and all are in the mutual thermal equilibrium with each other with the same uniform temperature beta. So we should now bring in another system like this qubit here, and it gets thermalized, where it just becomes one of those parts, one of those subsystems consisting the buff, right? It gets assimilated to the horde, the zombie horde. Okay. So now, so if this is how it's supposed to work, right? You get this thermalization, assimilation, spreading of the disease. Then okay, so this qubit now should have this ability, right, to be the vector for the further spread of thermalization. It's if it got assimilated to the buff, so now it's just like any other piece of the buff, right? So if I therefore, if I bring in some third system S, okay, and I couple it to the qubit, it should be the same as I would couple it to any other piece of the buff, right? So that the qubit can, forward the spread of the thermalization. So this is like this idea of spreading, right? And we want to see it, and we want to describe it. So let us do just that. Let us do just that. So we have our buff here. Boom. Okay. And we have our qubit, which is now assimilated. Let's say it can be thermalized, so it got assimilated. So we have buff here, B, temperature beta, and we have qubit Q, which also thermalized, so it's also beta. Let's write it like that. Ugh, cannot see anything. Let me redraw it. So we have a buff, a big buff, B, temperature beta, and we have our qubit here. I use the same color because to have this idea that it got assimilated. So it's also it thermalized, and now we bring in the next victim, unsuspecting system S, some generic system S, right? And let's couple it directly to qubit, but not any other part of the buff. Okay, and we want to see that once we do that, S will still thermalize to the same temperature as the buff, right? If we can show that, then we are happy that we managed to capture this idea of spreading thermalization, and all is well. The physical picture we painted with assimilation, stuff like that, is then correct, and it should work like that. That's like the all the statistical physics, thermodynamics teaches us that this is how it should work, right? And we should be able to capture this with our theory of open systems. Yeah. So let us define how this coupling works. So we have a Hamiltonian now for system S, for qubit, and for buff. So all parties involved. And now let's be, S is generic. Won't be very specific about it. So it has some free Hamiltonian H0. Uh, you know what? Let's just HS, call it HS, times 1 times 1. So, 1 in qubit, 1 in buff subsystems, plus 1 times the original qubit buff Hamiltonian, okay? Because, they are still there. Qubit and buff are still here. They're still interacting. We just know that this interaction will brings the qubit to thermal equilibrium. Uh, what else? Oh, and the coupling, right? This is important. So we want to couple some coupling strength mu. Uh, so some observable on the system S side, S times couples to qubit. Let's pick Pauli matrix Z to have something different than previously, and 1 on the buff side. So this is explicitly we are saying that system S interacts with the qubit, but not with the rest of the buff. And this is what encodes this, right? This kind of coupling encodes that. And then initialization, so let us initialize our SQB, t equals 0. Let's take some arbitrary initial state for system S times, and the rest, let's pick a thermal equilibrium for the total system qubit plus buff. So this guy would be then proportional to E minus beta H QB. Okay. Right. And of course we will assume weak coupling, right? Assume weak coupling. So mu times correlation time much smaller than 1, because we know we have our toys, a Born Markov approximation and stuff. So we want to use it. Besides, this is the only regime we talked about regarding thermalization. So let's stick to that. And in that case, the evolution of the state of system ST, okay, rho ST will be, well, approximation, because Born Markov approximation of Davis generator. This time we didn't simplify stuff too much, so the Davis generator for system S will be, in its full glory here, full complexity. So we'll have a part that's due to system S Hamiltonian, but it's shifted. This cannot be avoided here. So we have part due to the free Hamiltonian of the system plus the shift, and the Davis generator itself will look like this. Psi t sum over omegas. This time we don't have the general. I mean, we weren't cheeky. You have to sum over all the frequencies that appear in the system, energy level differences. So we have a lamp shift here, Q omega Q, because the coefficient here, the lamp shift is it comes from the qubit, right? From the qubit observable. And we have the Hermitian part as omega dagger S omega. So these are, the frequency decomposition of the coupling S, decomposition with respect to energy levels of the shifted Hamiltonian of system. So this like we did before, right? Plus the rest of the generator, again, sum over omegas, of course. And we have transition rates again with index Q because they come from the qubit observable. And we have all the sandwich here and the anti-commutator bit. Right? Nothing simplifies here too much because we are not specifying what the exact form of S is. That's it. Oh, and it acts on the initial state, 0S. All right, so, and it has a lot of pieces. We already seen them, analyzed them, and stuff like that. But the main question we are asking here: will the thermalization spread? Is qubit capable of being a vector for the passing the pathogen? Okay, pathogen. Will it be able to grab S and assimilate it to the buff, just like buff did to qubit before? And we know from our analysis of the dynamics of thermalization that uh, in order to get under those conditions, under the conditions that we are defined here, so with weak coupling limit, the sufficient condition for thermalization, sufficient condition for thermalization is nothing else but the transition rate WQ to satisfy D-Tate balance. Q minus omega, WQ omega, and this ratio has to be exp beta omega if we want the system S to thermalize to the same temperature as the buff temperature, right? The coefficient here has to be the same beta as this beta, okay? We know that this, if we have this, the Davis map takes over and will eventually bring any initial state of this guy of system S to thermal equilibrium, and thus giving us our spreading thermalization. Okay, so the question, so to check if this condition is satisfied, well, we just have to calculate WQ, and we know how to do this. We know our transition rates. Omega. It's a formula analogous to the one we wrote before. So it's twice. This time it's mu square, right? Because the coupling strength is mu. Real part, half of the Fourier transform as usual, and we take trace QB EIH QB T0 plus U, again, of sigma Z qubit. Yeah, I didn't do it implicitly or explicitly, so I have to keep in mind the shift, the coupling shift. EI minus H QB T0 plus U and EIH QB T0 sigma Z minus the shift times 1 minus IH Q T0, close the parenthesis. Sorry, I'm running out of room, times the initial state, which is stationary thermostate, close, do the Fourier transform, close the real part. So again, this is stationary, so I can get rid of T0. But this is a two-time correlation function, okay? But it's stationary, so it can be simplified. We can get rid of T0. Everything only depends on this time difference U. So the Fourier transform goes over U. So that this is the formula. But so, in other words, to check if we have a thermalization, we have to verify that transition rates satisfy detailed balance with correct temperature beta. Okay, but to get the transition rate right, we need to be able to calculate this two-time correlation function, and it's a two-time correlation function for the qubit only observable, right? It's sigma z times 1. So it's trivial on the side of the buff. So in other words, this is a two-time correlation function for qubit that is open to buff. Two-time correlation function for the open system. Okay? Which brings us to the problem at hand. Okay, so you would expect, the task to proceed, we have to be able to handle this uh, two-time correlation function or multi-time correlation functions in general for the system that is open to buff or environment and stuff like that. And you would expect that the theory of open systems will give you some, methods to do that, right? So I guess the only method we have really at the moment is to dynamical maps. Okay, so how do we apply dynamical maps, a dynamical map to actually calculate this guy here? And the answer is that you can't, because dynamical maps, by the very definition, the only thing they can do is to take initial state and propagate it in time. So they are good for calculating expectation values or single time correlation functions, right? So if the only thing we had was this, if we didn't have this guy, okay, we don't have this guy, then this would be the same as calculating the expectation value of qubit observable. And this is something we could, switch from Heisenberg picture to Schrodinger picture. So then is the evolution of state. So then we can, okay, so we just have to evolve the state of the qubit that is open to interactions with buff. So this is where dynamical maps comes in, and we have all the, we developed all the formalism and methods, approximations, perturbation theories to handle that stuff. But once you introduce this guy here, you cannot reduce it to just evolving the initial state. That's no longer, it doesn't work anymore, okay? And therefore, dynamical map methods are useless here. In other words, this multi-time correlations for open systems, including two-time correlation function, are beyond the scope of the standard open system theory, of the stuff that we looked at before. We have to expand the scope of the theory. Then we have to figure out uh, a way to actually use what we learned so far to apply it to be able to calculate things like this. Okay, so this is our and once we know how to do it, right, we can develop some methods, some perturbation theory to do the calculations. hopefully we can then look at this ratio. We can calculate our transition rate, look at this ratio and see if we are detailed balance is satisfied so that we can have we can have our thermalization spread, which we want to have so much. And that's not the only way, the only problem where nagrywa. So this is not the only problem where you have not the only problem where you can encounter multi-time correlations. It's actually only having the ability to do single time correlation or expectation values is pretty limited because you have things like linear response theory, you have like non-equilibrium transport, or even sequential measurements of systems. All those things, to describe them properly, you need multi-time correlations, right? Just having your dynamical map methods won't just won't be enough to do this. So this is a pretty important piece of the theory that we have to develop to actually have the ability to do the full description of quantum dynamics of systems that are interacting with their environments. So yeah, so let us do that. But before I start to thinking about solving the problem itself, let me do the formal introduction to multi-time correlation functions. Okay, so let me do some formal definitions, and once we have that, then we can think about proceeding with some open system stuff. So 7.2 multi-time correlation functions. So I will just abbreviate it with correlations. Okay, just to it's a mouthful, multi-time correlations. In writing, I will probably from time to time use a shortcut MTC, right? Multi-time correlation. So multi-correlation functions, but for closed systems first. Closed systems. So correlations for closed systems. Yeah, let's begin with the case when there are no problems. So to have a general correlation function, so you calculate it for a given sequence, given ordered sequence of times and observables. Okay, so you have to start by specifying certain sequence of timings. Assuming they are ordered, so Tn greater than Tn minus 1, greater than 1. So we have ordered timings, and we have a associated corresponding sequence of observables. So let me call them x. So we have some xn, x1. You can pick x1 equal x2 equal x3 and so forth. So you can do like an autocorrelation for one observable, but you can pick and choose. You can change them if you want to. Each one can be different. That's okay. And each observable xi is represented by some operator. So xi, right? It's represented by some operator xi. All right. What else? Oh, the one more thing. So these are, so we have sequence of timings, ordered timings. You have a sequence of observables, and you also have to specify the initial condition. Mm, initial condition. Initial condition, okay, at zero. Let's say it's at time zero, uh, uh, that won't curtail the generality of what we are talking about. An initial condition, of course, encoded in some with some density matrix rho, which you can always do the spectral decomposition. You can do a spectral decomposition for it, which will soon make extensive use of. So let's write down the spectral decomposition, index phi from 1 to d, s, so some dimension of our system. So you have eigenvalues. So this is I'm using the same convention as we used in a couple of lectures ago. So and eigenvectors, eigencats, let's use our let's use our group theoretical parametrization of bases. So let me write it like this: ITS. So the generators of basis transformations and the corresponding coordinate phi 0 that generates the transformation from some reference basis indexed by psi to the eigenbasis of operator rho 0. TS by 0. Okay. As you might expect, there probably will be some byte trajectories down the line when I'm starting to write my basis transformations with those generators T, you know what's coming. So to again use the same notation as before, you can abbreviate this projector here with a symbol. So we have our eigenvalues phi and the projector P S at space-type coordinate tau 0, which would be 0 time, and the basis coordinate phi 0 of projection on eigencat phi. Okay, and so we have our sequence of timings, we have a sequence of observables represented by operators, and we have initial condition. And now the definition of multi-time correlation function. Multi-time correlation. So MTC. So the symbol, this is the symbol I will use for them. I belonging to sets capital I plus X I T I plus. So this will be a complicated symbol, okay? Minus X J T J, but it will be worth it, okay? Close the bracket and specify initial condition rho. And this symbol, it means you take a trace with your system S, you take a product I belonging to the set I plus. You take your operators representing your observables in Heisenberg picture, Ti. Okay. But now, we have our timings here. So to keep order, we use time ordering here. We put a initial condition in the middle, j belonging to I minus x j t j operator time order again to order those guys. But after we order them, we apply the Hermitian conjugate. So it will reverse the order essentially. So this is the formula. So now me explain some stuff. So we have our timings, right? We have our sequence of timings t and sequence of observables, right? So we have this a sequence of indices from 1 to n, okay? And now those sets here, I plus, I minus. So we take those indices, we can take those indices from 1 to n, and we can redistribute them over between those two sets here, okay? And in such a way that I plus, when you take a set sum, set union, you will get the total set of indices, okay? So in other words, you take your timings and you distribute them into sets. One will be one set will be used as arguments for the operators going for, let's say, for the sequence going forward in time. The other set will be going for the sequence going backwards in time. I'm saying backwards because here is forwards because you take time. There's time ordering, right? So you pick your timings, and then time ordering will sort them from the latest on the left, the last one, the earliest on the right, to the right, and the other set, you do time ordering, but then you take complex conjugates, so you will reverse the timings. Okay. So this is the so this is this. What else? Okay, the Heisenberg picture of the operator. Take Ti. This is just with respect to the Hamiltonian of your system. STI, XI, STI. Okay. What else? Okay, so one more thing. So this definition of correlation function, you could use it for basically arbitrary operators X here. Okay, it could be whatever you can dream of, but we'll restrict ourselves here to X being observable. So operators, we will assume that there are Hermitian operators. So operators that have that can represent observables, real observables, and that operators that have well-defined spectral decomposition, just like density matrix over here. So we can, so for every xi of Ti, right, we have a spectral decomposition 1 to ds, the dimension, eigenvalues, small x, y, and we have our, we have a Heisenberg picture, and we have basis transformation parametrized with a corresponding coordinate phi I. So for density, for initial condition for the density matrix was phi 0. So for observable I, it would be phi I. Phi I dagger and the boosting time. And this, again, shorthand notation, projector PS tau I, which have time component Ti and the transformation coordinate phi I of phi. All right. Now this, if you really wanted to have a correlation function for non-observables, so for operators that are not Hermitian, you can still use those. Uh, you can still use correlations defined only for Hermitian operators, because if you take any operator A that's not necessarily equal to its Hermitian conjugate, okay, it's okay, because you can like define the x real part of this operator, A plus a dagger, or a Hermitian part, and you can define the like imaginary part or anti-Hermitian part, which you can call it a minus a dagger to I. Once you do that, A can be decomposed as x re plus I x im. Okay, and this guy x im is Hermitian, and so is x re by construction. And so if you want to have correlation function for A, you can just express it as a combination of correlation functions for its real part and imaginary part. Okay, so this is there is no we don't lose anything when we restrict the in our operators here to observables only, and we gain some stuff when we do that, as I will show you right now. Because these correlation functions, let me maybe, oh yeah, let me show you an example. Let's say, so let's hop in, back to our initial setup, right? So we had when we brought qubit to interact with the buff, the patient 0. Right, we had a transition rates WB, which half Fourier transform, blah, 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 of correlation function, two-time correlation function for the coupling, buff coupling B. So in the language of our using the language of multi-time correlation functions. So this guy here then, okay, this guy here. So we would write it using our symbol, our definition as B, so let's say 2 would be 0 plus U, T1 would be T0, okay? So this guy would be, we would write it like this, plus rho P B beta, okay? So this thing, we could write it, place all the timings into the forward in time forward in time set. Okay, but if you So why do you even need the this other branch, the times that go backwards in time? Well, consider the following example. Let's say you want to calculate change the color. Say you want to calculate for example, so we had this thing that we called I uh, alpha 2 T2, which was imaginary part of trace some F alpha 2 T2 T1 some row 0. So this kind of thing came up when we talked about uh, fluctuation dissipation theorem, or generally when we're figuring out the supercumulants, right? This is how uh, this is how the supercumulant, the information about environment coupled to our system, came in uh, through supercumulants, so things like this. So like this trace of a product of coupling operators at different times in their interaction picture, right, with initial condition, and we made a we looked at the imaginary part and the real part of this kind of trace, and we showed that there is a fluctuation dissipation theorem that connects them, which was then the source of the detailed balance and stuff like that. So uh, this kind of imaginary part, we showed that you can write it as 1 over I, a trace of a commutator of those two operators, alpha 2 T1 alpha 1 row 0. Okay, so this is then identity you can show. And so now in the language of multi-time correlation functions, because you see this is a trace, you have two times, you have row, this is two-time, some form of two-time correlation function, which you can, if you cast it in this form and you want to use the notation we defined here, well, that would be nothing else but 1/2 I F alpha 2, I guess, T2 plus F alpha 1 T1 plus row 0. And this translates into trace F, well, T2 alpha 2 T1 alpha 1, okay, row 0. But that's only half of this expression. The other half is F alpha 2 T2 minus F alpha 1 T1 minus row 0. So why minus all of the sudden? Well, let's break this down and show what's going on. So according to our definition, this guy equals trace row 0, and you have to sort them T1, alpha 2, T2. Okay. So you see, so this is forward in times because pluses, backwards in time because minuses. And now I can use cyclic property of the trace to move my operators to the left-hand side of the density matrix. But they don't commute with each other. So what you will get is T1 alpha 1, T2 alpha 2. So these guys, you see, the order is reversed with respect to this piece, right? And of course, when you take the difference between them, you go back to the trace of the commutator. So in other words, we need the second branch, okay? Without it, you wouldn't be able to, there is a difference between those, because operators don't commute with each other, there is a difference how you order them around, okay? So to capture stuff like this, so the average commutator or the imaginary part of this two-time correlation, you need the ability to have this split between pluses and minuses. And that's, many more examples can be found, but this is like the one we kind of seen before. So this is why we have this weird definition to capture all the possibilities with multi-time correlations, which there is a huge richness of options here. But the other thing, why I insisted on using this maybe overblown notation with parametrization of basis transformations. Well, because once you have your multi-time correlations defined in this way, it's very easy to embed them into the B trajectory formalism that we talked about in lecture lecture 9, I believe. Lecture 9, B trajectory formalism. Strikes back. Strikes back. Because this thing here, if you did this kind of expression and you use the spectral decomposition, it's a straightforward algebraic, one line of algebra to show that multi-time correlation functions are nothing more but moments of B trajectory distributions. So you can easily show that if you take your multi-time correlator minus x j t j minus with some row s, this can be easily written as sum over phi n tuple phi 0. Here you will have a product I plus x. So eigenvalues xi, sorry, phi plus j I minus x j phi j minus. Okay. And you take your bi-probability distribution. You get your coordinates. Coordinates, that those coordinates, okay, corresponding to the observables and timings. phi plus, phi n tuple minus, phi 0, and the initial condition rho s phi 0. Or if you want to use the master distribution, you can write it as an integral, functional integral form. Where is my cursor? So double integral. We have our kernel here. Where is it? Okay. Product I plus xi. So we switch to trajectories. So phi plus evaluated at tau I, space-time coordinate tau I minus xj phi minus tau j times, if we write it in terms of this master distribution, the initial condition comes in this form, eigenvalue evaluated at phi plus tau 0 times eigenvalue phi minus tau 0 square root. Now eigenvalues of density matrix are positive, so the square root works just fine. And we can use our master bitrajectory distribution. Phi plus, phi minus integration, functional integration over both components of bitrajectory. Right, so now once you write it like this, this split forwards and backwards in time, it connects pretty nicely with components of bitrajectory of your system. And this, so we had a notation convention for that, for this kind of bit trajectory average, if you recall from the lecture number 9 or 10. So product minus I plus xi capital phi plus evaluated at point tau I, coordinate tau I minus xj phi minus tau j, and we used here angle bracket with s to indicate that this is for system S, and this initial condition rho s. So this is the main motivation for the notation, by the way, because of the ability to embed it quite naturally with bitrajectory formalism. So what else? What else? Okay, so let's take a minute of break before we. So this was because this was the multi-time correlations for closed systems, right? We defined it for closed systems where everything is, there are no issues here. You just need to calculate Heisenberg picture of some couple of operators. There's no problems with calculating this expression here. And I just showed that you can, take this formula, this object, this mathematical multi-time object, and basically rewrite it in terms of bitrajectory formalism, which is cute. Okay, it may be cute, but so far it's not really helpful at this moment. it's not helpful yet because next, after the break, we will move on to the next step, 7.3 multi-time correlations open systems. Okay, this is where complications arise, and this is where a connection with bitrajectories becomes crucial, okay, for solving this problem. But let's take a minute of break. Okay, so let's get to it. All right, so now multi-time correlations, but in open systems. So the difference will be, we'll still be using this definition. These are correlations, but now let's take our system S and let's couple it to the environment, some generic environment, which will then, modify for us the Heisenberg picture, the form of the operators X and stuff like that. But still the same idea of multi-time correlations, but in more complicated system. So let us couple now. Well, let me change the color. I don't like this one. Maybe this one will be more. Okay, so let us S is now coupled to environment E. Yeah, so let's write down what we mean. So let's initial condition. Let us set it to be a product. So the open system standard. Okay. And the Hamiltonian, we will do the standard thing we always do here, almost always. So the bare Hamiltonian times 1 plus 1 times HE plus the most general form of the coupling. So alphas S alpha, right, times bare coupling E alpha. And we do all the shifting. So that let me write it here. So we get HS, shifted Hamiltonian, 1 times HE, nothing changes here, plus the shifted coupling, and I will use our notation from before, S times F, right, to indicate the shifted coupling goes from E to F, and the sum over alphas as this kind of inner product. And just as the reminder, what the shifts actually do. So shifted Hamiltonian is a bare Hamiltonian plus lambda sum over alphas, the trace over E rho E0 times S alpha, right? And the shifted coupling F alpha is a bare coupling E alpha minus the average value rho E0 times 1. And I'm assuming here for simplicity that the initial state for E is stationary so that we don't have to, so that the average is time independent. So we have we don't have this silly complication with time dependent eigenvalues and stuff like that. So this is all the standard stuff, okay? And now what will make system as open is because the correlations we will be interested in will be between observables that are S-only observables, okay? So this is what makes it what makes this problem into open system problem. So we take our observables. How do I want to S-only observables. So we take a sequence of observables X S such that the operator representing XIS is of the form XI times 1. Okay, so S only observable then. With let's say those are the same X's as here, right? So I will use my coordinates here, the same notation for coordinates as before, okay? So now, we modified our system now is this totality S plus E. Here is the Hamiltonian, there's interaction, the initial condition is defined, observables are defined as only observables. Okay, so let's just take some multi-time correlation for those observables and let's see what we'll get. So we split our timings in some general fashion. XIS TI plus product JI minus JS TJ minus and rho S rho E, just to remind us that we took the product initial state. So of course this thing here, if we take the bi-trajectory distribution for S and E for the total bi-trajectory, right? This will be some moment of this big bi-trajectory distribution. But this is for S only observables. So their environment, something has to happen with environment. It's like typically when you look at, based on our experiences, when you look at S-only stuff, the environment gets averaged over, right? So we are expecting to see something similar here as well. And we will. But we have to calculate this stuff a bit. All right, so let's just put in the explicit formula here. So the symbol is a trace over S and E because total trace, which trace over S and E, you can make it in sequence, first over E, then over S. But before we get there, let's write down everything. So we have the first piece, time ordering. We have a product of Heisenberg pictures of operators. The Heisenberg picture, this is our Hamiltonian. So EIHSE okay, and the operator representing our observable xi times 1, right? Close the picture, SETI. Initial condition, S times E, sure. time ordering, and we have the backwards in time branch, I minus, Heisenberg picture, SETJ, operator 1, SETJ, and the dagger, right? Because we have to reverse it, reverse the ordering. Excuse me, let me take a sip here. So now we are at this place. Of course, we will now put in our spectral decompositions of operators and stuff like that. Uh, and the comment I made about taking trace, right? So here in the formula, you take trace over everything, but you can defer taking trace over S to after taking trace over E. But now, once we do that, okay, so we have then an expression that is a trace over E uh, with fixed initial density matrix for E. This is just asking to be interpreted as a quantum average, right? We talked about like who knows how many lectures ago, the thing that brought us to the idea of bitrajectory formalism in the first place, right? So, back then we did this averaging, and this analogy with average, where partial trace and set initial density matrix. We use this for basically for the for the case of single time correlation function. Here, it's a similar scenario, but instead of single time, we have a multi-time correlation now, right? But we can do the employ the same tricks, same algebra we used before to transform it into the form that highlights this. I mean, exposes this analogy with partial trace as an average, right? Average over by trajectory. So I would so I will take this expression here and I will spare you the details, referring you back to the lecture 9, I think, where we did it for the first time, where we talked about it as an average. This partial trace is an average. So I just take those same, I will do the same moves here, but in this a little bit more complicated scenario. But the similar structures will emerge. Okay, so I start by taking the so okay. So what kind of tricks I will use here? So I will take a spectral decomposition, of course, of operators I, X, J, and I will rearrange a bit the evolution operators, and I will switch to interaction picture with respect to the coupling between the system and the environment. Yes, so that I can get the yeah, you will see what will happen. So I do this spectral decomposition plus the interaction picture. This leads me to the following inscription, following formula. So I will have sum over sequence phi n plus minus. This comes from spectral decomposition, phi 0. Then I have my eigenvalues, product of eigenvalues, xi of phi I plus. So this shouldn't be surprising. This is how we because this is a multi-time correlation. It is a moment of some bitrajectory distribution. So this thing will pop up always. Mm, and also the initial condition for uh, the eigenvalue of S initial condition by 0. So this all comes from the spectral decomposition of operators, S operators, okay? And then let me move to the next line because this one will be long. Trace over SE. So before I start to order the traces, I do the spectral decomposition. So now I also need the switch to interaction picture product over K n1. So this will be our order product of super operators. So I'm collecting the I'm collecting this thing here, right? You have a sequence of a product of operators on the left side of the density matrix of density matrices, and you have a reverse product of operators on the right hand side. So this is like you are sequencing taking a sandwich, right, with operators, with corresponding operators. However, here mm, if you want to do sandwiches, this is a similar structure we encountered when we first defined the bitrajectory distributions. But back then you had this. We had a. You took sandwiches, but those you always have a piece of bread at certain time, and you have its partner piece of bread at the same timing, but on the other side of the density matrix. Here, because this is multi-time correlation function, here is just some set of timings, and this here is some possibly different set of timings. So you look at this as like, sometimes there's missing one of the pieces of bread is missing, right? I cannot do the sandwich. However, to make a sandwich, you don't need operators X, you need projection operators, right? So if you have X's, we did the spectral decomposition, we will have there will be a projection operator coming from this particular xi at time ti, okay? But if we are missing a projection operator at corresponding time ti on the right-hand side, well, we cannot. If you want projectors, well, that's you can just multiply everything with identity and just decompose it into decompose this identity into projectors you need. Okay, because they are projectors. So even if you are missing the piece of bread, you can always slot it in. And once you do that, you have the stuff that's got the product on the left and product on the right. You can just turn it into taking a sequence of sandwiches, which will have the form of P S tau K phi K plus, and the other piece of sandwich at the same coordinates using the trick with identity, right? If you're missing a piece of bread, you can just feed it in with identity. If you do you do this filling, what you won't get extra eigenvalues, of course, right? That's why here you have just the same eigenvalues as the uh, original input operators here. So you have sandwiches uh, on the side, but we have those are S-only operators, right? So we are taking sandwiches, projectors, but only in S subspace. Okay. On the environment subspace, you don't have to do anything because there are only identities here. So this is the it's invisible bread on the side of environment, right? So times just identities. Invisible bread is the same, I mean, it's like not taking sandwich. Mm, and now okay, but now the evolution operators. We need to, which we gather together and switch to the interaction picture. So we have time ordering over S times F, right? The interaction generator in the interaction picture, the coupling Tk minus 1 Tk, and we get our S times F using the same notation same convention as in previous lectures, du. This is a interaction picture. It couples environment and system S. So it acts on both of them. So parenthesis, close everything. Okay. And probably need one more bracket to indicate. So you have this kind of structure. You have a sandwiches, okay, psi minus, psi plus, psi minus on one side, psi plus on the other side. So components will be trajectory come in, and identity in environment, and times a segment of evolution with this interaction picture propagator, okay, generated by the coupling, and you take them into a sequence, ordered sequence, right? And all those guys, they act on what? They act on, so we did the spectral decomposition for the initial conditions for system. So we have a projector here, tau 0, phi 0, okay, times, and let's leave environment for now, the initial condition for environment as it were. Oof. Okay. So this is what we started from this, and this is what I transformed it into. And now let me call this guy here, because we have here an object, a new object. A new but not completely new object. Let's call this guy, this trace, as Q S conditioned by E. Okay, phi n plus, phi n minus, phi 0, phi 0. Okay, because look, this is so we took multi-time correlation function for S-only observables. We know that this should have a form of a moment of bitrajectory distribution. But because this is a S-only observables, so we don't really need it. We shouldn't need the total the distribution for the total bitrajectory for S and E, right? So this should reduce to the bitrajectory. The formula should automatically get averaged over a environment specific bitrajectory, right? So after all is said and done, this should be a moment for x's, of course, but the distribution, the moment you are taking off, it should be bitrajectory distribution, and it it looks like it almost, except for this extra extra interaction term here. So it is like bitrajectory distribution. It distributes the phi by trajectory, the one that describes system S, but it is modified by interaction with environment. It's modified by like taking the extra average over environmental bitrajectory. And this is actually what's going on here. This trace over E. So we have here trace over S and E, right? And we have initial condition for environment, and we even have a bunch of this interaction picture propagators generated by the coupling. So we can sequence taking of traces. Let's Rather than taking the trace as a whole, simultaneously, let's first, before we take trace over S, partial trace over S, first let's take a partial trace over E. And this should give us some kind of average over B trajectory, the quantum average, right? And this is actually what's happening here. Uh, so let me write down so we have our QSE, QS conditioned by E of, let me, I don't know why I want to be clear about that. So our coordinates, let's make it explicit what is the symbol for time component, what is the symbol for the basis transformation component, and conditioned by T0, which is 0. And we have our arguments, sequence of plus arguments, minus arguments, and the initial. Right, and this is given by this formula, but now I want to turn trace over E into a partial, this trace into a partial trace over E first, which I want to turn into a average over B trajectory, which, everything is set up here. So I repeat the tricks. Let me get back to my color. So again, looking back to the lecture 9, 8, 9, and 10, I think, I look I'm looking at what I've done there, and I just want to repeat those steps here in this a little bit more complex scenario. And once I do it, I turn this into a average. So I'm taking care of partial trace over E and convert it into integral. Product K from N to 1. So I will be left with sandwiching here. Tau K, phi K plus. This doesn't go away. Tau K, phi K minus. All right. I'm switching to bitrajectory picture, so this identity here would be consumed. And now what happens with the coupling? Time ordered over dynamical variable z minus I lambda tk minus 1 tk z u psi plus, psi minus. So just like in those previous lectures, the coupling, the interaction picture transmutes into propagator generated by the dynamical variable z, depending on the byte trajectory representing the environment, which we are integrating over. Okay, so those guys, so this is what happened. So we have initial conditions on S, phi 0. Again, the initial condition for environment is also transmuted. What is transmuted into times, well, it's the usual beast. We have rho E, so eigenvalues of density matrix, initial density matrix, psi plus at time 0. So I will use the same notation as those lectures before. So the coordinate for basis transformation to eigenstates of rho E, the coordinate will be denoted by this fancy rho symbol, times 0 rho, square root as usual, boop, and QE. Psi plus, psi minus, E psi plus, E psi minus. So yeah, so I perform the partial trace over E before doing the trace over S, and I perform it by switching to the bitrajectory picture, where it's becomes the same as taking the bitrajectory average over the distribution of bitrajectories for environment as a free system. Okay. So we had a symbol for that. So this thing, therefore, is a trace over S. We have a product here, K n to 1. We have a sandwiching tk phi k psi k plus ps tk phi k psi k minus time ordered propagator tk minus 1 tk z u psi plus psi minus du, and we have the initial condition here by 0, and the integral. So we had a symbol for this, a bitrajectory average versus over system E. Okay. And the dynamical variable Z. What is dynamical variable Z? Well, it's the same as I have here in my notes that checkout equation 219. The same form of dynamical variable as the one we introduced back there. So we basically took the stuff about byte trajectories from when we were looking at dynamical map only, and we reuse all those concepts to treat the multi-time correlation function right now. So we obtained that for open system, the multi-time correlation for this system's observable is a moment, but the moment of byte trajectory distribution that's not of this system alone, but of the system that's modified by the presence of environment, hence QS conditioned by E. And this modification over environment comes in this form as a extra average over environment. And the coupling between and the coupling between system and environment comes in the form of these propagators generated by the dynamical variable z. And that's the and when we have this form of multi-time correlation function for open system, now we can start no, now we can build our theory, okay, how to actually now take this guy and figure out how to actually make it computable, okay? So that we can, at the end, maybe answer our question about propagation of thermalization or any other question involving multi-time correlations, which are plenty. All right. So yeah, let's move to the next bit then. 7.4, temporal correlations of the trajectory. Um, so so the thing So the thing that we are gaining here by switching all this problem, formulating this problem of multi-time correlations, uh, so shifting the problem of multi-time correlations to a problem of calculating this by trajectory distribution affected by environment, which is then, turned into a problem of basically calculating this average over environmental by trajectory. And the main benefit from doing that is now that we have this form, okay, uh, it has this, it explicitly looks like, you have this like composition, the sequencing of a propagation, okay, of propagators, like interrupted by an intervention, taking this sandwich here, okay? And then you have another period of propagation, and another sandwich, another period, and so on and so forth, right? And the thing that is crucial here is that because we have a bitrajectory psi of environment, right? We can like keep track of the temporal correlations between the periods of propagation, okay? Right, so there is some, stuff going on here on this between time tk minus 1 and tk, due to the coupling. Then you have this interruption, and then you carry on the propagation, but those two periods of propagations are related to each other, correlated to each other, right? And the correlation comes in it can be the tool for bookkeeping of these correlations, of quantifying them, is this underlying bitrajectory, right? That binds everything together. So this is like the key element of the key conceptual element that will allow us to actually formulate some rules, some theory for calculating all this stuff. Uh, so if you believe me, if I'm convincing to you that the key thing about this whole reformulation is to keep track of correlations. So, based on our previous experiences, you probably can guess immediately that, well, if correlations are of some importance, then probably cumulants will come in, right? I mean, cumulants come in almost always, but here it just asks, and you say correlations, temporal correlations, you are, in my mind at least, you are, okay, so where are the cumulants, right? So just a reminder, what are the cumulants? So, uh, you know, if you start with moments, okay, one, you have some tk psi plus psi minus. So we have a moment of dynamical variables, okay? And cumulants came in, were defined by taking those moments and which are statistically reducible and decomposing them into statistically irreducible elements, decumulants, right? So the following decomposition can be treated as a definition of cumulants. So we had this P partition of the set of indices. Then we had time ordering over dynamical variables, and then we had this products over sequences belonging to P, to partitions, and this is where cumulants came in, right? Z, T, P, K, Z, T, P, 1. Right? If you look back to the times when we talk about cumulants, right, we figure out immediately that for by trajectory distributions, you also have moments, you have cumulants that is parallels, analogies with stochastic processes all apply here, and those cumulants, quantum cumulants, by trajectory cumulants are also irreducible, so they can serve as a proper way to quantify correlations. Uh, so having that, uh, basically, excuse me for a second. Sorry about that. Noise from the outside. Uh, so if you look at this problem as a problem of accounting for correlations between propagators, so I would, if you adopt this kind of point of view here, then I would say that what we did so far in this lecture, the dynamical map, the part where we talked about dynamical map. So I would say that what we did there was we developed some methods for uh, taking care of uh, correlations, temporal correlations of bitrajectory that are confined within a single propagator like this. I'm saying this because if you look at, so let me write down so let's say dynamical map between time with index I, okay, ti minus 1, which dynamical map, it's a you can express it as this bitrajectory average ti minus 1 ti for our dynamical variable here depends on size du, right? So this is the form. This is what we back in those lectures we talked about this bitrajectory formalism. This is what we essentially what we showed, right? That the dynamical map is a average bitrajectory average of this kind of propagator, right? Generated by the dynamical variable z. And this guy, I can write it down as a decompose it, expand it into a series. So I can expand it into series because it's exponent, time-ordered exponent, but that's okay. No problem with that. dun ti minus 1, u2, du1. And we have here a average attacks the products. So we have a moment here. kn1 z u k psi plus psi minus e, right? So this kind of moment here, which we can rewrite it as a bunch of. We can decompose them into cumulants as well. No problem. un I minus 1 u2 du1 and just plop in the plop in this sum over p capital p belonging to p and cumulants zp k blah 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 z up1 cumulants. Okay, right? So this is dynamical map. Dynamical map is basically you can look at it as okay. So the issue, if you want to calculate this, you have to figure out what to do with those cumulants that are rolling, connecting with each other inside this dynamical map. Okay, here. So basically, uh, our supercumulant expansions and all the other perturbation theories that we were talking about there, you can think of them essentially as some kind of methods that allow us to, in some systematic way, to decide which cumulants we want to keep and which we want to get rid of, right? And once you decide which we want to keep, you want to keep inside your propagator, right? This is what will inform the rest of your moves, right? The shape of the perturbation theory you're using. So, for example, if you are doing a lowest order Born kind of approximation, you're saying that, okay, let me disregard everything except for the second cumulant or something like that. Right. So clearly our previous efforts were focused on dealing with correlations, aka cumulants inside the single period of propagation, right? And so it's fairly obvious now that when you move to multi-time correlations, now you are dealing with new situation where those correlations, those cumulants, are allowed to, they are still present here. They are still, boiling inside this period of propagation, but now they are allowed to spill out and connect to other propagators, right? That otherwise would be like disconnected or interrupted by this kind of intervention, like here, right? So now, not only you have to contend with, take care of correlations inside the period of propagation. Now you have to figure out how to connect them in some systematic way, right? In such a way that you can actually compute something. So this calls for new kind of approach. Uh, and the approach I want to show you, I want to advocate for, is something. It's something that it's based on something that I call a hierarchy. Hierar, hierar. God, it's difficult to write it. Hierarchy of correlation strength. Okay, so this is the concept I want to introduce for you, and this is the concept on top of which we'll build, or based on which we'll build our uh, a perturbation theory for handling the connections between propagators. And the idea is to like use this relation between moments and cumulants, and to like, but to not to just take a moment and expand it into purely cumulants, or take a cumulant and expand it into just moments, but to mix and match this stuff. So, and in the process to create this kind of like a hierarchy, a combination of, let's say, diagrams, where you have like blocks of dynamical variables that are like connected. You form a whole network of connections through cumulants between those blocks. And, then you can like order them or put them into a hierarchy where the most complicated, most total connection is on the bottom, and like the simplest, most trivial connections are on the top. So in mathematical inscription, what I'm talking about is, let's start with taking a moment, arbitrary moment of our dynamical variables, plus one, z tr, z t1. Okay, so here, just to keep a notation more manageable, I will make a dependence on by trajectory implicit, right? So I should write it as psi plus, psi minus, right? But I will just skip the dependence. All right, skip the dependence of by trajectory. You just assume that it's there, okay? So I took an n time moment of my dynamical variable, and I'm splitting it in my head for now. Later on, we'll find the reasons for doing this that are more tangible. Like imagine that I split this moment into like two blocks of timings. Okay. So here times go from Tn to Tr plus one. Okay. And this block you have from Tr to T1. Okay. So I have those two blocks. Now I want to like split them into this network of connected blocks by using the relations between cumulants and moments. The fact that I can express cumulant as a combination of moment, but also moment as a combination of cumulant, so I can like go in between a little bit. So I'm writing this the following way. So first term, I take the first term will be where the blocks are disconnected. Sorry, R plus 1 times Z R Z T1, okay, plus. So this would be like a, say, zero order, where two blocks are not connected. Zero order. The next element, the next bit in the hierarchy is when you take those two blocks, but you connect them by through one cumulant. Okay, so we will have a sum over index j and index k. Maybe let me be more precise. So j that goes from that scans the left block, and you have sum over k that scans the right block, the second block, and you have a moment here, tj ztr plus 1 r tk zt1. Okay, and those two guys are connected through cumulant. So because I need the second order cumulant to make this connection, I can use my contraction notation that we used before, right? So that would be a, like, let's say, first order. And then you have to, you go further. Then you have like a sum. The next would be sum over j prime, k prime. You have your block tj prime e ztk prime, and you have let's say this one connects with this, so you have two pairs, two connections. Okay, then you can go and take three connections, four connections, until you exhaust all the blocks, right? And then you go even further, where you say not pairwise but triples. You take cumulant, you connect the two blocks with cumulant of the third order, then third order plus second order, then third order and third order, fourth order, and so on and so forth. You construct your whole hierarchy, and then on the very bottom, you will get, I mean, once you get into the bottom, you will start, I mean, on the very, very bottom, you will have where everything is connected with everything, finally, and on the very bottom of this hierarchy, you have a full cumulant. tr plus 1, tr, t1, okay? And this would be nth order. How do you exactly, order in this hierarchy? This could be second order, but you move further down the line, it becomes debatable what is the third order. How does it look? Is it like 3-time cumulant, or it's like three pairs or something like that. It's a then it's kind of debatable what you want to do. Uh, but the idea, so you obtain this hierarchy by basically taking this relation and just playing around with it, right? So you have, moment can be expressed as a combination of all the cumulants, but now you take at the sum, look at the like sub-sums in it, and you can realize that you can get some of those cumulants and reconstitute them back into a moments while leaving some other cumulants as they are. And when you go back and forth like this, you can decompose any moment into this kind of form. So it's hard to explain how to do it. I mean, how to go for how to exactly mechanically go from this to this. My best advice, I think that the advice I can give you is like uh, try doing it yourself. So start from something simple, for example, four times, fourth order moment, split it in half, and just write down explicitly this decomposition into cumulants. Okay. So you decompose your fourth moment into all the combinations you need to get the cumulant expansion for it. Then write down for yourself a second order moment, decompose it into cumulant, and third moment, decompose it into cumulants, and then go back to your original fourth moment and start collecting the terms so that you will start to reconstruct the combinations of cumulants needed to expand the third moment, second moment, and so on. And you will see that you figure out a couple of examples like that, and you will see that this is the general form that you will get. If you take your moment and in your head you split it into two blocks, you can always do this kind of decomposition of this hierarchy of two blocks, starting from independent blocks, factorize moments, and you connect them with more and more complex and mm, a more complex net of connections, right? And those connections are realized through cumulants, which here are represented by contractions. Here it's just because we need to take a cumulant of everything, it's just looks like this. And now the idea behind this whole decomposition is that, so we have those two blocks, and now imagine you start moving them apart, okay? Uh, and now we know cumulants have this the cumulants, we talked about this previously. Yeah, we talked about this previously. So the cumulants have this property, right? That when you bring them apart, the dynamical variables start to decorrelate, right? And they decorrelate completely if you move everything further than the correlation time, right? But you start moving them apart. You're not reaching correlation time yet, right? But the correlations between those two blocks start to weaken, right? And the expectation is that the things on the bottom of this hierarchy will decay the fastest. The lower you are on this hierarchy, the faster you will decay as you are approaching the correlation time. Okay. Why? Well, because the irreducibility of cumulants is that this guy, for it to survive, all the dynamical variables has to be correlate with each other, right? But now when you start moving the blocks apart, you have like all the variables in one block and the other blocks, their correlations become weaker simultaneously, right? So it's like the weakening of correlations get multiplied here, right? The more things are connected, and the more things start to decorrelate simultaneously, the more destructive the effect. That's the expectation, at least. Uh, so in this sense, when you're moving apart, you start approaching the correlation time. The guys from the bottom of the hierarchy will start to fall first, and like the last survivor, of course, you move them very apart. You get the only the zero order. Everything is decorrelated. Moment is factorized, but before you get there, guys like the first order guy will be the least. It will be weakened by. It will be less weakened than the guy below. All right. So, in other words, if you are taking this, the idea is that once you take this moment of ours, it is split into those two blocks, right? Split in those two blocks. And when the blocks like reach correlation time, right? The split, the delay between them is like getting closer or around the correlation time, the time scale of correlation time, the like the lowest you will get the complete the correlation, so the moments factorize, and the most important correction to this complete decorrelation, so aka the one that survives the longer, would be the first order of our hierarchy. JK, ZTN, ZTJ, R plus 1, TR, boom. So single cumulant connecting the two blocks. And you can imagine that if you move them even further, the the connection between, let's say, the Tn and T1 will fall off even faster. So you can even imagine that this will you move even further. So this will like go into something like, you have decoupled blocks plus something that's like, you only connect the stuff, the most important stuff, the one that's least decayed would be the thing that like connects the very edges of the blocks. Okay, so that this is the idea. So now that we want to we want to construct a perturbation theory around this decomposition, this hierarchy, right? So because we are like our task is to figure out how to connect propagators across the interventions here, right? Uh, and we want to like make it computable. So we want to set up some kind of perturbation theory. What this perturbation theory will be about? Where natural thing would be perturbation in the orders of this connectedness of moments. All right. So that's the basic idea behind the approach. Uh, so let's do it then. So let me switch to different color, blue. So we move to the next bit, 7.5, a perturbation theory for multi-time correlations. Well, in open system. The next section, and we start of course at the zero order. Let's analyze zero order first. Zeroth order. Make it the subtitle the quantum regression formula or QRF, quantum regression formula. All right, so how do we imagine zero order? Well, I think it's pretty plain. So the idea is that if zero order, according to our hierarchy, zero order are blocks that are not connected at all, right? So if you apply this, if you want to apply this to the problem of our by probability distribution, right? So this is like here we have a propagation. So this is what propagators define for us, the blocks of timings, basically, right? So this is one block from tk to tk minus 1. And then it's like a natural place where to split them is this intervention. And then you have another block that goes from tk to tk plus 1, right? And everything is under the average, right? So you have this huge, if you want to see moments explicitly, just expand those exponents into power series, and you will get like combination of these huge moments. Natural border between the blocks is then defined by those interventions. And you say, okay, so zero order would be to neglect all connections across the interventions. So in practice, what it would mean, you take this total average of this whole product here, and you just split it into a product of averages. So let me write it down then. So the idea is so you take your QSE, tau n, tau 0, phi n plus, phi n minus, phi 0, phi 0, which again equals to the trace over S. And let me, just to save me some writing, this guy here, this intervention, let's give it a symbol P because it's a super operator, so calligraphic font PK. Okay. K, so it's just all the variables are the component K of each of the variable. So we have average of product, K M1, intervention, and we have propagator tk minus 1, tk, zu, e, ps, ps 0, right? So now if I can take this if I take the propagator here, right, and write it down as a k, maybe L, from 0 to infinity, minus L, do the expansion here, ZU, ZUL, ZU1, okay? Uh, so then I can rewrite this whole average as a combination of huge moments, right? So I go to so I explicitly go to the this kind of situation as I have here. The blocks, how do I split into blocks? Where the place to split is of course when the intervention happens. So you have your blocks that span times from TUL to TU1, from TK to TK minus 1, right? And you have just all those combinations of blocks. And you say, okay, zero order is, I just neglect all the connections across the interventions. So I have to just take all those blocks and just factorize moment for them. Uh, so you do the factorization, trace S, KN1, PK, sum L0 infinity minus I lambda L TK minus 1 TK du L U2 TK minus 1 du1, and we have moment here. U1 brackets acting on this projector here. But this I can just take the series and transform it back into the exponent. So this is approximation, right? This would be zero order. So I have trace, I have composition, I have interventions, and I have TZ minus I lambda TK minus 1 TK ZU DU average, because we factorize all the moments, 0, trace S, PK, and intervention. And this guy here is something that looks like a dynamical map, right? A dynamical map in this sense, right? So this is this zero order approximation. It's typically it's called in literature quantum regression formula. Okay, so it's basically this is where you neglect the connections between periods of propagation, okay, across the interventions, and you can couple this. I mean, okay. So this is zero order approximation. Zero order in terms of it is a zero order approximation in terms of this hierarchy here. Okay. But you can also show that it is a zero order in terms of weak coupling regime as well. Because now, if you to explain what I mean, okay, so what if you think about it, what kind of the next order correction to this approximation would look like, right? So this approximation is built around the idea that you neglect all the connections across the interventions, right? So to get like the first correction to this, go to first order, well, you have to like include at least one of those connections, right? This is where the first order correction would come from. So in other words, the things you would be considering then would look something like you have some intervention at some time tj, and you have your moments, and you have some zu. I don't know what kind of letter to use here. UK, and you have some other z UI or something, and they are connected, right? That would be the source of next order corrections. And those guys, they are surrounded by other dynamical variables, more interventions and stuff like that. And you like integrate it, right? You will also have some integrals over those time variables here. So if you squint a bit, you can see that this kind of thing is of order, roughly speaking, it scales like lambda times correlation time squared. Okay, because each coupling comes in with lambda, right? And this is a connections through cumulant. Cumulants have finite range, so this integral cannot stray too far from this point here. Not further than correlation time. Same for this one. So the overall magnitude of this kind of correction would be something like lambda correlation time squared. So if you are working in weak coupling regime, this is small. In other words, the zero or for this zero order in terms of hierarchy of correlation strength, a perturbation to be a good approximation, it is necessary that you work in weak coupling regime, right? So T core E small. So this is a necessary condition for this perturbation to contemplate of this perturbation to be even a valid approximation, right? So if you want to do something where do this hierarchy of connected of connecting this hierarchy of connecting blocks of propagation, for this to make sense, okay, for this to be, for this hierarchy for you to be able to cut off this hierarchy of some reasonably low order, you basically have to work in the weak coupling regime, right? But if this is the case, this weak coupling regime here, it should also apply to the dynamical maps we have here, okay? And in fact, yeah, you can, to be consistent with your approach for the, this multi-time correlation perturbation theory, you have to work in weak coupling. So if you are already in the weak coupling regime, you can look into you go to zero order, you get your split into dynamical maps. So now you can just, okay, so I am in weak coupling regime, so I can apply my standard weak coupling regime approximations to those isolated now dynamical maps as well. In this way, you can argue pretty robustly that this guy you can go further and approximate this guy with some, you know, Born Markov kind of approximation. Go to Davis propagators here. And the quantum regression formula, as it's used in literature, it actually applies to not only zero order hierarchy, but also with the application of Born Markov kind of approximation to each segment of propagation. So uh, so this is what once you do both those things, so this would be what people call quantum regression formula. Okay. But this is the zero order, right? I already like sketched how do you go to the first order connection. So let's just be more explicit about it. And let's consider the next order correction. So 7.52 first order beyond QRF, beyond quantum regression formula. So again, zero order, zero, zeroth order is when you take um, zero order is when you neglect all the cumulants connecting propagators across the interventions P, right? CU du or N1 PK U TK TK minus 1, right? The dynamical maps, you split them into just isolated dynamical maps. So if you want to go beyond that, right, you want to go to the first order, well, first thing first, we have to like think a bit, and we have to identify what kind of correct connections from our hierarchy we want to involve here. So there are a couple of things. So, weak coupling regime, short correlation times. We are thinking about short correlation times. We can also we can also we can also assume, let's say, that the the correlation time is short in the sense that if you take any tk minus tk minus 1, that this thing is much longer than correlation time. So the blocks are long in comparison to correlation time. So coupling is weak, correlation time is short. So if you want to go beyond zero order and you want to connect some of the propagators, uh, you should take only a single connection from the top of the hierarchy, right? So one cumulant connecting them. And you probably don't need to bother yourself with connections that go across multiple interventions. So you just want to connect propagator with its neighbor, okay? And the lowest order approximation will be when you connect only like you include one connection at the time, okay? So in other words, the and all the of course all the connections, all the cumulants that exist inside each each block of timings. This is, you leave them as they are because this part is taken care of by our previously developed methods for dynamical maps, right? Because once you are here, there are cumulants inside, but you have your methods to take care of them independently of the issue of connecting propagators across interventions, right? For example, by doing the Born-Markov approximation. So to make it more concrete, so let me write it down. So we have our in1. So this is the problem we are starting with. I minus 1 ti zu du, right? So this is the full expression. You have the propagators, interventions, and everything is averaged. Let's take subtract from this the zero order. Ti minus 1, okay. And out of those guys, so we basically take this, we subtracted all the non-connected bits that contribute to the zero order. And out of so we are left with all the possibilities of multiple connections across many interventions and stuff like that. But we want to focus on a single connection at the time and only with your neighbor. So let's discard everything except for terms that can be written as in this form, n minus 1. So we have Pn product j goes from n minus 1 to I plus 1. So we have map here, tj plus 1, tj, intervention. So I'm rearranging things a bit. Then we symbol delta p. Okay, I will define it in a second. And this guy is multiplied from the other side by product, sorry, k, I minus 1 to 1, intervention k, and the unconnected, disconnected map. So this delta p, I'll write down in a second. This is what this guy here will contain a connection across single intervention. PI index. PI. So what is the delta PI? So it looks like this. So I have average z minus I lambda, so propagator, ti plus 1 ti zu du, of course. So we have one segment of propagation, we have an intervention at point I, and we have other propagator, ti minus 1 ti, right? Propagators are sandwiching the intervention, du, minus the trivial zero order disconnected, completely disconnected part. ti minus 1, all right? So here again, this in principle contains all possible connections for possible orders between those two propagators, but we want to focus on only single connection, single cumulant. So this we can neglect everything except for this case when there is only one connection. So let us expand those propagators into series, subtract this trivial part, and neglect everything that has more than one connection between the two blocks interrupted by the intervention. So what you get here, you can write it as sum over k and l goes from 0 to infinity. This sum comes from the expansion of exponents. You will, of course, have all your integrals. I plus 1. So one block we've integrated over timings u du1, and the other set of integrations, let's call it dvl, di minus 1 to v2 dv1. Okay, so those are integrals. And then what do I have here? We have of course, couplings, k plus l, coupling strength. And now we have additional sums. We get, right, so we expand, so we have a moment here and moment here. We take only one connection, but in each term you have multiple options for which variable from block 1 you connect with which variable from the second block. Hence the sum, additional sum. And I say that this goes from R1 to K, and the other sum R prime goes from 1 to L. One block scanning first block and the second block. And well, you have the UK, ZUR, ZU1, E intervention at point I, ZVL, ZVR prime, ZV1, and those are connected. Okay. The rest we neglect. And now we can do some cool stuff with this thing, because this equals to and now, so we expanded two exponents, right? We expand this exponent and this exponent, and now we took a connection here. So we like knocked out one of the dynamical variables from each of the expansions, right? But now, if you look at the structure of this double series, you can I mean, again, you would have to like experiment a little bit on your own with this, but you can see that there is let's say if you fix everything that happens uh, from here to here, and from here to here, and from here to here, and just focus on the terms in this double series that change the number of z's of dynamical variables that appear just in this segment. Okay, and you will see that there will always, in this reservoir of terms of the series, you always find enough terms to for all those other segments fixed to reconstitute inside this little segment another exponent. Okay, and then you can do the same for all the other bits. Okay, so you have to play with this on your own, but you should get to the conclusion that there is always enough terms to, and they will exhaust all the terms in the process to basically expansion knocking out of pair of terms, but you can still reconstitute new exponents here, and here. Everyone else, you can just gather it up into new set of exponents. So in other words, all this stuff, after everything is said and done, you have minus lambda square, because all the other z's and other alphas and other integrals will be absorb into those new exponents we are reconstituting. But you will be left with those two connected z's, so two lambdas and two integrals will be left. So this is those two lambdas and imaginary units with them. You will have an integral that goes from ti to ti plus 1. So this is, one of those integrals, one of the integrals that integrated over a time variable of uh, a connected z. Let's call this integration variable as t greater. And you will have, of course, also an integral from the other block, from the other piece, other pair. Let's call this d less, t less, t more, t less. And you get here reconstituted exponent that goes from t greater to ti plus 1, zu du. Then you get your z t greater, the one that's connected. And you have another reconstituted exponent that goes from ti to t greater. So they are hugging the connected z. Du, du, close, average, intervention, open average, reconstituted exponent that goes from t less to ti, zu du, zt less, and the final bit goes from t less to ti minus 1, zu du close average, and the connection. So this is a cool thing you can show, right? It has a very nice structure. But we can do more. We can do even more. Right. So couple of things. We can simplify it even more. This is a cumulant. This connection is a cumulant. So this has a range. Correlation time is a range. The maximal range of those two integrations. So you are moving those integrations tell you that you move those dynamical variables, and if you move it to the left, this exponent shrinks because you move this guy, you also move its lower integration limit, and you increase the integration limit in this guy, right? You move other way around, you do the opposite, right? You stretch this guy, squeeze this guy, and same here. But now, those two variables are held together by the contraction, right? So they cannot be moved further than correlation time, or the cumulant vanishes, right? So non-zero contributions are only when the distance between the greater and the lesser is smaller than correlation time, right? So those two integrals, they move around those dynamical variables, but really what's going on is you are just squeezing those two exponents here. You're just squeezing them more or squeezing them less, right? You cannot give them more room than correlation time to breathe, right? Because otherwise the contraction will cut off everything. So in other words, this exponent here, this integral here, is just this guy here. Basically it scales like e to minus I lambda t correlation time, okay? Something like that. Well, times z ti, let's say, okay? This is what you are allowed to do, but this is small, right? Because we have weak coupling regime. So in other words, this squeeze exponent here is more or less identity, right? Within the weak coupling regime, you can basically treat it as a identity, and at the same time, you know, you're squeezing this guy and you're stretching this guy, so that, but since the variation of this t, I mean the difference between this t greater and the original limit ti is, the difference is around correlation time anyway. So again, if you can neglect this one, you can also basically say, okay, the correction, the error I will make when I replace this real limit with ti, the original ti, will be some small correction that is higher order in the coupling in lambda times t core. So this guy can be you can safely stretch this guy to go from ti to ti plus. Okay, and you can do the same thing here. This approximated with identity, and here you take this upper integral and just stretch it to ti. All right. So in weak coupling regime, this simplifies further, and you can then write it as et z ei lambda from ti, the stretching, right? Zu du. I can close average here because I'm neglecting the squeezed guy completely. And this variable sits inside the average, but it's contracted, so it's not it's not affected by the average anymore. So if I neglect this guy and stretch this guy, I can just take the average and just move it past the contracted variable. So I take the coupling constant here. I take my integrals, those integrals, ti plus 1, okay, dt greater. I take the other integral, ti minus 1 to ti, t lesser. I take my contracted variables, pi, z, t lesser, contract them, okay? And now, this one is neglected, this one is stretched, so I just have another sandwich here. Du. Okay. And I'm not done yet. There is more we can do. Look, this is a finite range. It has finite range of correlation time. So again, this integral, its upper limit is at ti, and lower limit of this guy is ti, right? So this integration over greater, it goes to ti plus correlation time, and beyond that, it just cuts off. And same with this guy. It goes to lower, to ti minus 1. I mean, the ti, sorry. On the lower limit, the lower limit is again, the lower limit is limited by correlation time. So this integration goes from ti to ti minus correlation time, essentially, right? Because then it's all cuts off naturally. We are assuming here that the difference, so ti plus 1 and minus ti is much greater than the correlation time, it's much longer than the correlation time, and same for here. So naturally, the upper limit here and lower limit here, we should stretch beyond the correlation time, essentially, right? But because the cumulant, because here we have a cumulant with finite range, even though in principle, you could go beyond the correlation time with both integrals, they will get naturally cut off at the correlation time. So in other words, what is the actual value of the upper limit and lower limit? It doesn't matter because they will get cut off at correlation time anyway. So you can just take those guys and without paying much penalty, you can just stretch them to infinity, and this guy to minus infinity, because it will the real value of the limit here doesn't matter because it will get cut off much earlier anyway. So you can just say, okay, so it does not depend on this limit anymore anyway. So I can just put here a universal limit of plus and minus infinity, right? And another thing is that those are just dynamical maps, right? So the final move is to say that we have here u ti plus 1 ti. Here is our correction, ti plus infinity. Let me just change the name of variables. Minus ti, tv. We have our contraction, u pi zv contract, and we have the dynamical map on the other side. Okay, so it's almost the final form, but this is good enough. So this, again, what we are working on. So this was this delta p, okay? And we showed that this delta p turns into this kind of sandwiched by the contraction intervention pi at time ti, okay? Uh, and this whole correction is actually it itself is it's stuck in between the dynamical maps, isolated dynamical maps, right? All the connections, uh, all one connection that we are allowed to take in the first order approximation are here. It's here. It's confined here. So now we take this guy back and put it back in. We get our result. We get our result for the first order perturbation. So we can write it as sum over I from 1 to n, Pn product k n minus 1 to I plus 1, isolated map, Ti, Tk, sorry, Tk minus 1, intervention, okay, close. The correction itself, so the isolated map from Ti plus 1 to Ti, right? And we are scanning over index I. What else? And the correction itself, minus lambda square. We have those integrals that we stretched. dv zu intervention at point I, contraction, And we close it with the other part, one more isolated dynamical map, right? So dynamical maps go to the point, it goes to TI, this starts at TI, and there's this correction. It's like it appears as like just a modified intervention. So let me just before I make this comment, let me close this final bit. U T K T K minus one. All right. So using the fact that we are working in a weak coupling regime and that the stretches, the time blocks between interventions is long in comparison to correlation time, or to put it differently, correlation time is coupling is weak and correlation time is short. We managed to derive a first order approximation that looks like, behaves like you get a something that has a form of zero order. So you have interventions, you have isolated dynamical maps interspersed with interventions. And the first order correction modifies this by at you know at each point in time you take a sum of terms where in each term there is a one point along this sequence where the intervention is modified, okay, by this single contraction, integrated contraction. So it's still, it's kind of like intervention, but with dressed intervention, which makes it much easier, to handle this whole expression. And there are one more thing that we can do to make it even more computable is realize that we assumed at some point at the beginning, we assumed that the environment is stationary, uh, and we can use this to our advantage to even get rid of this dependence on TI, okay? And the thing you can do, so I check out equation 386 in the script for details. I will just write down the result. So if you use the fact that environment is stationary and you recall the frequency decomposition of the coupling operator, and of course you write down what dynamical variable is explicitly, which we will have to check out the notes to see what its explicit form is. But what you will get, Ti plus infinity du, you will get something that's maybe not super pretty, but it's much easier to handle. So you will get the following thing. E minus I Ti H S bullet. So like a free evolution. Then you take sum over alpha 1 and alpha 2 and sum over omega 1, omega 2. You take S alpha 2 omega 2. Then you get a the original intervention, but with time knocked out. You don't have to worry about time. We've taken care of it. Phi I plus PS 0 phi I minus. Okay. Times. There is another combination of super operators. So I have here a coefficient C alpha. It depends on alpha 1 and alpha 2 and on both frequencies. This coefficient multiplies a commutator omega 1 alpha 1 but dagger bullet plus I imaginary unit coefficient K omega 2 times an anti-commutator S omega 1 alpha 1 dagger bullet close. And well, that's not all, unfortunately, because you have to close it with e to I ti hs. Oh, actually, no. This is like Heisenberg picture. This plus and this minus. Okay. Or not Heisenberg picture, interaction picture, but in super operator form. And so this is, I think this is the simplest form I can make it. It should be ripe for computation. I mean, this is something you could compute, a matrix of which you could actually compute. We eliminated time ti, this ti we relegated it to this, interaction picture kind of transformation. So now the question is, okay, so what are those two coefficients? This is where the information about environment actually comes in. And they are similar in form, and they kind of complicated, but I don't know how to transform them even further. So we use the fact that we have stretched our integrals to infinity. Du minus I plus I, sorry. Sum of frequency, no, difference of frequencies, U. There is other integral that goes from U to infinity, dv, ei omega 1 v and r, coefficient r, v0 and k. It's all this stuff is the same, except here comes coefficient I, v0. And those coefficients R and I, well, those actually was prescient enough to use them as an example. Remember this one from the like 2 hours ago? So it's imaginary part of this two-time correlation function for buff coupling observables, right? So I is the imaginary part, R is the real part. So coefficients I and R are the things that are related to each other through fluctuation dissipation theorem. This is where the origin of detailed balance and stuff like that. So they come back, those two correlation this is so R and I, this is where the naked information about environment comes in into this whole formula. And again, because this is the lowest order approximation, it comes in the form of a two-time correlation function of mm, environmental observables. Uh, and you have to do some pretty nasty stuff to it. But it's something that you can in principle compute if you have, let's say, R from you get it from something. You can get I through fluctuation dissipation theorem, for example, and in principle you could just execute this integral. It's not maybe even analytically with some approximations if R has a simple enough form. So that would be the first order approximation, and you could going through similar motions, thinking about higher order corrections in terms of those, the connections from the hierarchy of correlation strength. You could set up some kind of diagrammatical approach to this whole stuff. And if you want to go beyond that, here are the tools. You can use them, depending on your problem. But here I will stop on this first order correction. So together with zero order, so we take first order and zero order, and those two we can combine them to get our by trajectory distribution. And when we have this by trajectory distribution calculated to this first order, then we can take its moments to actually calculate the multi-time correlations of observables that we needed, right? And we have another section here in the notes, 7.6, where is application to the problem of thermalization propagation. Spreading. Right, because this was our initial problem, right? We wanted to see if the qubit that was assimilated by the buff will be able to spread thermalization further when you take some system S and couple to it. And to check, right, for sufficient conditions for this to happen, we figure out that in weak coupling regime, you have to check for detailed balance in transition rates. And to get transition rates, you have to calculate two-time correlation function for qubit observables. For qubit that is coupled to buff, right? So qubit is an open system. Now we have our methods, we have our perturbation theory. So the section 7.6 is where you can find the fairly detailed calculations of what you have to do. Even more details are in the paper I referenced you to in the very beginning. But I would just say that once everything is said and done, you do the calculations, and to get analytical formulas, you can make an extra assumption that temperature is actually high, so beta is small. And once you do all that, you can get a formula, and the formula is that WQ minus omega, WQ omega. So in zero of order, you will get that it's 1. Okay? If you didn't include this correction, so you just use the zero order, the quantum regression formula, okay? So you neglect all the connection between the across the interventions, and you can also deploy Born-Markov approximations to each isolated isolated propagator, a dynamical map, which I wrote it down, very simple dynamical map from the very beginning of this lecture. You can do all the calculations and you will get that WQ, the transition race is symmetric in omega, so the ratio is overfixed to 1, which is bad because 1 is not E beta omega, even if beta is small, okay? I mean, it's formally, okay, this does not violate detailed balance per se, uh, but it predicts, because, if beta was 0 actually, then detailed balance would be this, right? The ratio would be 1. So it's kind of, you can say, okay, it doesn't violate detailed balance, but it uh, zero order zero order perturbation predicts infinite temperature for the bath. So you would get thermalization of S, but you would thermalize to the wrong temperature, which is, which is not good. This is not what you want. So this is zero order, which is bad. Okay, so what happens if you go first order? So first order, which is, again, it is very crude approximation, right? Because we took the simplest correction from the based on our hierarchy, and we did a lot of weak coupling, this squeezing, this stretching. We neglected a bunch of stuff, stretch integrals to infinity, yada 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 yada. We did a lot of very crude approximations here. You could improve them significantly if you wanted, and also I will assume here is small. I'm assuming here that beta is small. Beta is small, high temperature limit. And then you get actually that this ratio does become dependent on temperature. Okay, it's not 1 anymore. There is a temperature dependent correction, but it doesn't look like exp. Well, does it though? If beta is small, beta omega is small, well, you can expand it into series. So you can run beta omega plus 1 over 2 beta omega square. And if you stop at third order terms, because beta omega is small, uh, those first three terms are the same as the expansion approximation of E beta omega, if you notice. Okay, the third order is there is a difference there. It's a little bit of difference, and it gets worse the higher orders you go. But for high temperature, in high temperature, those you can neglect them. So this is like this for high temperature is very close to uh, the correct detailed balance ratio. Okay, and again, you shouldn't expect much. I mean, it's already pretty amazing that you get something like this because it was just the most crude, the most primitive application of this perturbation theory. I wasn't fine-tuning anything here. It's just just take this stuff, take the simplest stuff. You do a lot of approximation on top of that, or Markov on top of that. A lot of stuff you do here, and still the lowest order correction basically recovers detailed balance, which means that we get back our spreading of temperature of thermalization, which is this is what we expected. This is what intuition demands, and another fields of physics would suggest strongly that this has to happen. So this is like indication that this approach has some merit to it, right? And You can expand it even more if you want, just like with a perturbation theory for dynamical maps only. This Born Markov, for example, is very crude, right? But you can, using supercumulant expansion, you can make it even finer approximations. And I think that, speaking of supercumulant expansions, the stuff I was talking about here, so the perturbation theory based on this hierarchy of correlation strength, right, which we used to calculate corrections to correlate multi-time correlations or by probabilities, which then can be used to calculate correlations. Right? We use this to figure out how to handle connections, correlations across interventions, right? But whatever you do, the zero order, first order, and go beyond, you will get something, I presume, something that will look like this anyway, right? So you have some effective dressed interventions. If you play your cards right, you will have some effective interventions, corrected interventions, but you will still have those isolated dynamical maps. And this, you can do whatever you want to those dynamical maps independently of what you are doing to those connections between them across interventions. In other words, the perturbation theory for dynamical maps, the supercumulant expansion, and the perturbation theory for the connections, for the multi-time correlations, they are related, but they are, they are correlated in the sense that if one works, I mean, if you have weak coupling regime, you have a justification for using one, and you have a justification for using, let's say, Born Markov approximations for those isolated dynamical maps. But it's like how far you go, what kind of approximations you actually use to dynamical maps after you get your dressed interventions, it's free choice. You have a free choice here. So in other words, the stuff that we did for dynamical maps is not wasted because it's still useful even in context of multi-time correlations. Because once you take care of the correlations across interventions, you still have to deal with correlations inside propagators. And there you use techniques and methods we developed for dynamical maps. So, you need both pieces to have the complete method, complete description here. And with this final comment, I think we can finish the lecture. Yeah, so there will be one more. There will be one more lecture next week, where I will talk about some final fun. I hope hopefully fun physical consequences of of a theory how we developed so far. Byte trajectories will again play a crucial role here, and yeah, but let's leave that for the next week, for the last lecture.